Before any human eye ever saw Neptune, human math predicted it. It was the first planet located entirely through mathematical calculation before visual confirmation. In 1846, astronomers noticed unexplained irregularities in the orbit of Uranus. French mathematician Urbain Le Verrier calculated another massive body was exerting gravitational pull, pinpointing its theoretical coordinates. When German astronomer Johann Galle pointed his telescope to the exact location Le Verrier provided, he found the planet on his first night of searching. This validated the theoretical model, proving a massive world resided at the edge of the system. Before we roll into the terrifying supersonic winds of this blue world, take a quick second to hit that subscribe button so you don't miss any of our cosmic journeys. All right, let's dive back in. This chart breaks down the baseline chemical composition of Neptune's atmosphere. It is composed of 80% hydrogen, 19% helium, and a critical 1.5% concentration of methane. Uranus shares an almost identical atmospheric makeup, including that exact methane concentration. Yet Uranus presents as a pale, washed-out cyan. Neptune, however, is a vivid, deep cobalt blue. Scientists calculate that an unknown secondary chemical component, or perhaps a uniquely thick haze layer in the upper atmosphere, absorbs red light far more efficiently here. From its mathematical prediction to its unexplained hue, the visible surface of Neptune is the result of invisible, highly complex mechanisms operating beneath the cloud deck. Orbiting an average of 2.8 billion miles from the Sun, Neptune should be a frozen, inactive sphere. Instead, it operates a massive internal heat engine. Its neighbor, Uranus, aligns with expectations, possessing a core radiating almost zero internal heat. This chart highlights the paradox. Neptune radiates 2.6 times more thermal energy into space than it absorbs. The source is trapped primal energy. During formation 4.5 billion years ago, violent accretion and gravitational contraction generated immense heat still locked inside the core. This escaping residual heat acts as the singular driving mechanism behind the extreme atmospheric dynamics we observe in the upper cloud decks. Just below the outer atmosphere lies a highly pressurized fluid mantle composed of a dense mixture of water, ammonia, and methane. Deep within this liquid layer, thermobaric forces reach extreme thresholds. Pressures exceed 200 gigapascals, alongside temperatures climbing past 2,500 degrees Celsius. Under these conditions, methane molecules are compressed, stripping away hydrogen and isolating the carbon atoms. Free from the hydrogen, these carbon atoms instantly bond with one another, crystallizing into rigid, pure diamond structures. Because these solid diamond formations are denser than the surrounding fluid, they sink. Millions of tons of solid diamonds continuously rain downward through the hot liquid mantle toward the rocky core. As billions of these heavy diamonds plummet through the pressurized fluid, their rapid descent generates tremendous mechanical friction. The friction from this falling material acts as a secondary kinetic heat source, meaning the internal chemistry of the planet actively generates new thermal energy to feed its own heat engine. When that intense internal heat travels outward and collides with the freezing vacuum of deep space at the outer atmospheric edge, it creates a highly volatile weather engine. This map displays the equatorial jet streams. The thermal differential whips atmospheric gases at 2,100 kilometers per hour. This metric breaks the sound barrier on Earth and doubles the wind speeds recorded on Jupiter. This supersonic atmospheric flow generates massive, high-pressure anticyclonic vortexes. The most prominent example is known as the Great Dark Spot. This schematic model illustrates the sheer size of the storm. The Great Dark Spot covers an area large enough to swallow the entire planet Earth. Unlike Jupiter's iconic Great Red Spot, which has persisted for centuries, Neptune's storm systems are chaotic and temporary. They vanish completely and then reform at different latitudes over a span of just a few years. The chaotic, turbulent cloud deck is the direct physical consequence of extreme internal heat forcing its way out into space. Beyond the atmosphere, Neptune anchors a chaotic lunar system consisting of 16 known moons. However, the mass distribution here is highly irregular. A single moon, Triton, accounts for 99.5% of all the orbital mass circling the planet. As this orbital map illustrates, Triton possesses a glaring mechanical anomaly. It is the only large moon in the solar system operating in a retrograde orbit, moving in the exact opposite direction of its host planet's rotation. A retrograde trajectory dictates that Triton could not have accreted alongside Neptune. It is a rogue dwarf planet that originally formed in the distant, icy debris field of the Kuiper Belt. Billions of years ago, its trajectory brought it too close to the ice giant, resulting in a violent capture event within Neptune's immense gravitational field. The sudden introduction of a massive dwarf planet into the local gravity well completely disrupted the existing orbital mechanics, shredding and destroying Neptune's original native moons. Triton is an alien hostage to the planet. Its presence proves the extreme, destructive reach of Neptune's gravity well. Surface temperatures on Triton sit near -235 degrees Celsius, making it one of the coldest objects ever observed. Yet beneath the crust, it remains geologically active. The moon exhibits an active state of cryovolcanism. Subsurface pressure builds up beneath the frozen exterior, eventually forcing liquid nitrogen, dust, and methane compounds to breach the crust. These eruptions violently expel material out into the moon's thin nitrogen atmosphere, creating massive geyser plumes that reach up to 8 kilometers in height. But the mechanics of its capture guarantee its eventual destruction. Because of the tidal friction generated by its retrograde orbit, Triton's momentum is decaying, causing it to slowly spiral inward. In roughly 3.6 billion years, Triton will cross the Roche limit. Neptune's gravitational tides will rip the moon apart entirely. Stems from a single historical event, NASA's Voyager 2 flyby in August 1989. For the first time, researchers received direct close-up imagery proving the existence of the supersonic cloud bands and the planet's faint dusty rings. In its brief passage, the probe also provided the sole visual confirmation of Triton's volcanic ice sheets before accelerating out into deep space. However, a fleeting pass at high speed leaves heavy gaps in the data. We lack crucial, long-term observations regarding how those storms evolve or how internal heat transfers through the mantle over time. The current scientific model of this violent ice giant is built almost entirely on just a few hours of proximity recorded more than 3 decades ago. To solve the remaining atmospheric equations, space agencies are actively drafting blueprints for a dedicated flagship mission targeting the late 2030s or early 2040s. The primary mission architecture involves delivering a deceleration probe directly into the cloud deck to measure the friction and composition of those 2,100 km/h winds. Simultaneously, an orbiting module would utilize long-term radar mapping to penetrate Triton's icy crust, searching for the vast liquid oceans theorized to exist beneath the surface. Neptune functions as a massive, self-fueling engine, where internal mechanical friction drives supersonic weather and maintains a gravitational well strong enough to snare and shred entire lunar systems. The cosmos is full of anomalies, and Neptune is leading the pack. Until next time, keep looking up.